Hi, my name is Scott Simpson, and today we'll be talking about one of my favorite topics, quantum numbers. So this is for students in general chemistry. The quantum numbers fall out of quantum mechanics, and you really need a full semester of physical chemistry, along with up to Calc 3 and differential equations to truly explain where these numbers come from, to get to the bare bones of where they come from. But we're going to discuss a general overview of these quantum numbers. So there are four of them that are given letters. We have n, which is the principal quantum number. We have L, the angular momentum quantum number. M sub L, the magnetic moment quantum number. And M sub S, the spin, electronic spin quantum number. And there's a set of rules that's used to describe these. We'll talk about those rules. After we discuss the rules, we'll explain what these numbers actually mean. So a lot of times in general chemistry, you're just given the rules and told, okay, know these rules, but there's an inherent understanding that one should know to truly grasp what these quantum numbers mean. And there's a lot of power in these quantum numbers. They explain why there are 3p orbitals, why there are 5d orbitals per energy level. When you're doing electron configurations, why do they look the way they do? So let's get into the rules. So n can be any whole number integer larger than 0. So any whole number larger than 0. And there are a large possibility that they can have. The value of L can extend from n minus 1 to 0. The value of M sub L goes from negative L to positive L. And the value of M sub S, there are only two possible values. It has to be either negative 1/2 or positive 1/2. And what these numbers do is they describe an orbital. These cameras staying out of focus. They describe an orbital or an electron in an orbital. So we know from the Heisenberg uncertainty principle, which states the uncertainty in position and the uncertainty in momentum has to be greater than h bar over 2, which is a constant. So what this is saying is we can't define exactly where an electron is. So we use these set of quantum numbers to determine this. So let's look at a set of quantum numbers and let's figure out if it is valid or invalid. So question: is the following set of quantum numbers valid? So we'll have A, B, and C. A, we have n is equal to 1, L is equal to 0, M sub L is equal to negative 1, M sub S is equal to positive 1/2. We'll have n is equal to 2, L is equal to 1, M sub L is equal to 0, M sub S is equal to negative 1/2, and we'll have n is equal to 3, let's go with. L is equal to 0, M sub L is equal to 0, M sub S is equal to positive 1. So now we look at this set of quantum numbers and we have to determine, is it valid or is it not valid? So what we should do is we should follow the hierarchy. We should look at our rules, starting with n, because all the numbers stem off of n. So n can be any whole number larger than 0. If we look at all of our sets, in fact, they all have an n that's greater than 0, and that is a whole number. Okay, so all of those are good. Next, we have L. The possible values that L can take on are n minus 1 to 0. So if we have an n that is equal to 1, the possible values of L that we can only have 1, which is 0. So the only value we can have is 0. That one's okay for now. If we look at n is equal to 2, what are the possibilities that we can have? Well, we can have n minus 1, so in this case 2 minus 1, which results in 1. So we could have 1, 2, 0. So 1 or 0. In this case, we have a 1 there, so we're good to go. N is equal to 3. Let's think about the possible values of L that we could have. For an n that is equal to 3, remember the rule is n minus 1 to 0. So n is equal to 3, n minus 1, 2, 1, or 0. So in this case, this value of L is correct. We're good. So can't rule any of them out yet. Let's look at the m sub L. The m sub L value can go from negative L to positive L. So the m sub L value completely depends on our L value. If we look, we have an L value that's equal to 0. We can only, again, go to plus or minus L. Since L is equal to 0, m sub L cannot equal -1. So this is incorrect. ML must equal 0 in this case. So this one is not valid. In this case, L is equal to 1 for choice or for set B. So what are the possible values of ML that we could have? Remember, we go from negative L to positive L. We have -1, 0, and positive 1. If we look, our m sub L value matches up here, so this one's good to go. In this case, for part C, we have L is equal to 0. M sub L has to be equal to 0, so that's okay. Then we look at our last quantum number, m sub S. We can either have -1/2 or +1/2. In this case, if we look at both of these or all of these values, they're all valid. So these bottom two are valid. Well, set A is invalid because m sub L had to equal 0 in that case, and it had a value of -1. So this one is not valid. Okay, so those are the rules, but what do these numbers mean? What's their physical representation? What importance do they have in chemistry? Why are we using them? So that's what we'll talk about as I play around with this game. So n again is the principal quantum number. It's the principal quantum number, and it's incredibly important because it stems off all the other ones. The original place that this comes about is from the Bohr model of the atom, where you have a nucleus, and you have an electron that would bop around in an orbit, and that n value was equal to the energy level, or in this case, the shell number. So the way you can think about the principal quantum number is a shell number. These cameras spazzing out. There we go. This is the shell number. And it can be approximately thought of or related to, it's proportional to, let's do it that way, distance electron is from the nucleus. So it also keeps track of the energy level. L we stated was the angular momentum. Quantum number. And what it describes is the shape of the orbital in question. Describe shape of orbital. Okay. So let's go through those and describe those in a moment after we discuss what ML sub is. So ML, again, is the magnetic moment. Quantum number. And what this describes is the orientation, the way that that orbital lies in space. So orientation of orbital. Okay. So we already discussed this principal quantum number. It's talking about the energy level, the shell number. The angular momentum quantum number, L, is describing the shape of the orbital. Let's go through and discuss each of the shapes that we have for different orbitals. And in this case, we're going to only go up to d orbitals. There are f orbitals and g orbitals as you go. So L values. The first one we're going to look at is where L is equal to 0. When L is equal to 0, what we're talking about is an s orbital. And there is one s orbital per energy level, so per value of n. And remember, each orbital can hold 2 electrons. So since there's only one s orbital, that means it can hold 2 electrons in total. Each orbital holds a spin up and a spin down electron. Okay, now the shape of this guy, it's spherical, it looks like a beach ball. Okay, so we talked about L is equal to 0. Let's talk about L is equal to 1. These orbitals, we're talking about the p orbitals. And we said previously that the 1s orbital there's one s orbital per n, per energy level, and it holds 2 electrons in total. When we're discussing the p orbitals, we know how many orbitals that they should have per energy level. When we do that, we know that there are 3 p orbitals, or you may not know that, per energy level. And remember, each orbital holds 2 electrons, so that means 2 times 3, 6 electrons in total can be held in the p orbitals. Now, why are there 3 p orbitals? To answer that, let's consider the possible values of ML that we can have. Now remember, the rules for ML are that you can go from positive L to negative L. So our L value is equal to 1. Let's write out all the possible values of ML. We have -1, 0, and 1. So what these are describing is they're describing the different orientations that those orbitals can have. So if we write these out, the p orbitals, they kind of look like dumbbell shapes. We could call this one the px, this one the pz, and the py is going to come extending out towards us. We're going to try and draw it on its side, looking down that way. So you can see, because there are 3 possible orientations, that gives us 3 energy. There are 3 orbitals. Now let's consider the next set of orbitals. We're going to move up on our L value. We went from 1, let's go to 2. In that case, we're going to go up to the d orbitals. And the d orbitals, they have some kind of strange shapes. One of them looks like a p orbital with a donut around it. And then there are ones that sort of look like butterflies. This is the dz squared. In this case, let's call this one the dxz. And then there are actually 3 more of these. There's the d, y, z, d, xy, and dx squared minus y squared. So when we look at these, if we count them up, there's a total of five d orbitals per energy level, per m. So remember, if we consider how many electrons can be held in total, we have 5 orbitals. Each of them can hold 2 electrons. So we got 10 electrons in total. Okay. I previously said that that we have 3 p orbitals because we have 3 possible values of ml. Let's consider what our values of ml will be if we have an L value that's equal to 2. So remember, m sub L goes from negative L to positive L. So we could have -2, -1, 0, 1, and 2. And if we look, how many different values is this? We count that up, 1, 2, 3, 4, 5. That's 5 different values, hence 5 p orbitals per energy level. Okay. Now, previously I said we use these numbers to describe electrons in a system because we can't talk about their position due to the Heisenberg uncertainty principle. So let's look at an example. So question, write out a set of quantum numbers to describe an electron in a 3D z-squared orbital. Okay. In that case, we have to write out a set of quantum numbers to describe this. So we have to know an n value and L value. So n is equal to, L is equal to, we need an m sub L, and we're going to need an m sub s. Let's look for information that's important to us. Let's first understand what we're trying to do. We're trying to write out a set of quantum numbers to describe an electron. That's important because if we're just describing an orbital, we actually don't need this last m sub s value. Since we're talking about an electron, we could have positive 1/2, or we could even talk about another set, ms negative 1/2. So those are possibilities. Okay, so now we're talking about a 3dz squared. So this right here, this tells us our n value. And this portion along here, that d tells us our L value. And then that z squared, since we specified exactly what orbital we're looking at, that tells us that we're speaking about one specific m sub L value. So our n value, we can easily see, is 3. So we fill that in, 3. Our L value, we have to consider what type of orbital we have. If we look back at our notes that we just took, we said L, when it's equal to 2, we're talking about a d orbital. So since we specified this as a d orbital, our L value must be 2. Now finally, our m sub L value, that depends on which orbital we specified. In my courses, I don't really make it so you have to memorize which ml value it is to put here, but as long as it's unique, it's okay. So in this case, we have to follow our rules. Let's call this z squared an m sub L value of 0. Okay, so we've written out 2 possible sets of quantum numbers for an electron in a dz squared orbital. Okay, so I hope you grow a greater appreciation of these quantum numbers and understanding what they mean. I will be producing a video on electron configurations, which will hopefully help that electron configuration idea sink in a bit deeper. By understanding these orbitals and these quantum numbers, you actually know a lot about the electronic configuration or the way the electrons reside in an atom. Thank you for watching, and if you have any questions, please leave any comments below. Thank you.